Hello, my name is Lucas. I'm a data scientist and I work at Arinti. And the topic of today is the steps to take in choosing the best machine learning algorithm for your problem. So I'll try to keep it simple. I won't go in any of the mathematics behind the algorithms, but I do make the assumption that you have some background in data science to follow what I'm talking about. I'll go through it rather quickly. You can always pause the video if you want to, and I'll definitely invite you to further explore concepts that you don't know about yet in your own time. So I'll be making a rough outline, the roughest outline of rough outlines actually. You can take year-long courses on this, but I'll try to keep it under 20 minutes. Even before exploring the data, what I usually do is I think about some questions that I ask myself, and the answers to these questions will lead me towards choosing the best algorithm for my problem. Questions are listed here. We'll go through them one by one. And in the end, we'll go through a little example together so then you can see my thought process in action. So the first slide, I'm already getting a little bit sidetracked. The topic of today is how to choose the best machine learning algorithm, but you should always first ask yourself, do I need to use machine learning to solve the problem that I have? If you're making predictions, you want to predict some unobserved outcomes, and you want to achieve the highest accuracy as possible, then go ahead. Machine learning is the way to go. However, if you're more interested in the making inferences about the population and you have a certain hypothesis that you want to test, then don't dismiss the standard, the classical inferential statistics too quickly. I myself, as a data scientist, when I'm faced with a problem, I'm tempted to immediately split into a training and a validation set. But if this is your real goal is to test a hypothesis, then it might make more sense to simply use the rigorous steps in the inferential statistics hypothesis testing instead of going the machine learning route. Keep in mind, this is not black and white. Machine learning can also be used to draw inferences about the population, and also any statistician will tell you that you can also make good predictions using those inferential statistic models. So you then definitely don't have to use machine learning. But in general, if you are making predictions, then let's talk about machine learning. Okay, the first question we have to ask ourselves after we've decided that we want to use machine learning is, are we using supervised learning or are we using unsupervised learning? And the distinction is rather simple. You simply have to know, do you have a labeled data set or do you have an unlabeled data set? For example, only a couple of weeks ago, I was working on a case with hockey players, and I wanted to know whether certain players were at weird positions during the game, and I only had a data set of relative X and Y positions without an outcome variable. Then this would be a typical unsupervised machine learning algorithm where we're simply looking at anomalies throughout the game in this case, only using some predictor variables. However, consider the case where, for example, a hockey coach already went through the entire data set and annotated moments in the game where he or she thinks that something weird is happening. Then suddenly we have an extra variable, an outcome variable, and we'll use that to predict the anomalies in the data set, and then you turn your unsupervised learning problem into a supervised learning problem. Keep in mind, unsupervised learning is often performed also in the context of supervised learning. So for example, when we're exploring the data set in a supervised learning problem, or when we are performing dimensionality reduction, this is also unsupervised learning. So yeah, you can use unsupervised learning in preparation of performing supervised learning, if that makes sense. Next step is to decide on, are we doing classification or are we doing regression? Also a fairly simple step. Regression is when we are predicting a continuous value, and classification is when we are predicting a discrete category or a probability of a discrete category. For example, I'm thinking about if you're predicting stock prices and you're predicting the value of the stock price in the coming weeks, then this is a regression problem because you have continuous values. However, if you're simply interested in predicting whether the stock price will go up or go down, these are discrete categories, so now we have a classification problem. Keep in mind, you can turn most, if not all regression problems into a classification problem. For example, if we have the continuous value in the same stock prediction example, but we're actually only interested in predicting whether stock prices will go up or they will go down, then we can use those values to turn them into categories and make this problem, in this case, a little bit easier. So simply something to think about, really think what is my problem and what is the easiest and the best solution for this problem. Even if you have continuous values, it might be more logical to turn them into discrete categories. And also you have some examples of typical classification and regression algorithms listed here below. Most algorithms have an extension in the other type of models. For example, logistic regression is an extension of linear regression and so forth, but it's not always the case. So today I'm also focusing on supervised models. So I won't be talking anymore about the unsupervised models. So right now we've decided that we're doing machine learning. We have a supervised model and we either have classification or regression. Then we have to consider the amount of data that we have available. Some models simply need more observations to perform well than other models. And then people usually ask, how much data do I need to fit a model well? And then, yeah, that really depends on the problem that you have. The amount of data is also always relative to the amount of features that you're working with and the complexity of the problem. So you always have to consider, for example, if I have 1,000 observations and I only have one feature that is very good in explaining the outcome variable, then I would say that I have a lot of data because I have 1,000 data points for this single feature. However, if I would have 800 features and they're all kind of important in predicting the outcome variable, but I only still have 1,000 observations, then I wouldn't have a lot of data. It's all relative to each other. So you always have to consider both the complexity of the model that you're fitting and also the complexity of the problem. And complexity of the problem, I mean usually the dimensionality that you're working in. In general, less complex model with more assumptions, they work better with little data, if it's correctly specified, obviously. Why? This is the famous bias variance trade-off. If you think you're going to be overfitting on your training data sets because you have very little data points, then you need to introduce more bias into your models, or else you'll be overfitting and your predictions on your validation data set will not be good. Also, vice versa, if you have more complex problems, so usually in a higher dimensionality, then you will need more data for these more complex problems. Always try to get as much data as you can. So more is always better, assuming that the sample data follows the same distribution as the population data. And also this here is relative to the amount of features that you were working with. So you can get more data. For example, data augmentation, often used in image classification, where they start turning and improving the contrast on certain images to get more unique images. But you can also get more data by decreasing the number of features that you have, for example, with dimensionality reduction or regularization techniques. So less important features also become less important in the model. So relatively, you'll have more data available. This is also always a good idea to look at the learning curves. Usually, most people only look at them in a neural networks context, where you fit both the train and the validation loss over the number of epochs that you're carrying out. But you can also do this with any kind of machine learning model, and then on the x-axis you would have the amount of training data, and this would really give you a good intuition about which models need more data and which models lead to a very fast convergence. This plot right here, it's not a good plot because it doesn't show convergence at all. The validation error will always be higher than the training error. So you need to fix that first. And then afterwards, you can start looking at how much data do I need to get to this convergence. Here I'm also talking about compute time. This is also something that you should consider. I'm talking about it together in the context of the amount of data that you need. Why? Because they are very related. The compute time usually will be higher if you have more data in a more complex problem case. So for example, if you have models that work fairly well with relatively little data, so it's always a good idea to fit a learning curve. Usually this is done in the context of deep learning, where you look at your train loss and your validation loss over your epochs, but you can also do this with any kind of machine learning model, and then on the x-axis you would have the amount of training data that you would need to achieve convergence. In this graph right here, we don't have convergence because the loss is for the validation always remains higher. But usually what you want to do is first make sure that you get good convergence, and then you can investigate with these kind of graphs how much training data you need to achieve this convergence. And this really gives you a better intuition towards which models need a lot more data to perform well and which models really achieve this kind of convergence rather quickly. Here I'm also talking about the compute time, so I grouped them together with the amount of data because they're all really related. It also depends on the model complexity and the problem complexity, so makes sense, more complex problem and more complex models will require more compute time. Why is this important? For example, if you want to do real-time predictions for a model that needs to work in real time, then you really need to consider the compute time of your model. I listed some examples here of models that generally work better with fewer data points and will have faster compute time, and also models that in general need more data points to perform well and will have a slower compute time. Also here, this is not black and white. You can have complex regression models, and for example, neural networks, you can make them as simple as possible, but in general, they'll only fit a neural network in a specific complex problem, so the compute time will also be higher as well. Something else to consider is whether your data set has whether your predictors have a linear relation or a non-linear relationship with your outcome variables. In introductory data science courses, you'll often see graphs and images like this, where they say if you want to know whether you have linearly separability in your data set or not, then you simply graph both of your predictors in the case that you have two, color in your outcome variable, and then if you can fit a straight line through them, then I would use something like logistic regression because that fits a straight line. If it's not possible, then you need to look more towards these nonlinear, often tree-based models that use partitioning in the dataset and end up in a nonlinear partitioning. This is not realistic. Usually in real life, we're working in higher dimensions. So how do you decide whether you have a linear or nonlinear relationship? You simply have to have a little bit of an intuition. You need to investigate the literature, look at similar problems as the one that you're facing, and see which models work best in that case. So this will also give you an idea whether you have to use a linear or nonlinear model. And also you can, if you really don't know, then you fit models from both groups. Carefully fit models from both groups. So really go through all the correct steps of tuning the hyperparameters, for example, and selecting the correct settings for your model. And then if, for example, the nonlinear model type would perform a lot better, then you can really start focusing on the nonlinear and really explore that a lot more, because that would mean that you can make the assumption that there's non-linearity in your data set. In practice, in general, in real life, you usually will see that most interesting problems will have non-linearity, and linearity, perfect linearity, and even general linearity is rather rare in real life. That's also, for example, in neural networks, why you use these activation functions to impose non-linearity in your model, why simply in real life most models tend to be non-linear. So something to think about. Lastly, but not because it's not important, I listed the interpretability of your model. It's also something you should always consider. I put it here in last place, not because it is not important, but mainly because other methods exist to make a black box model more explainable. So this image here is also something you'll often see in a lot of data science courses, where one model is considered to be more explainable and another model is considered to have a higher accuracy. Not sure if accuracy on here is really a correct way to describe it. I would put complexity on the y-axis. And they say this because, for example, in a linear regression, you really know how much each predictor contributes to the outcome variable, and in the boosting algorithm, then simply out of the box, you don't know this. However, you can, for example, in a random forest, see how many splits have been made on average over all predictors to see which feature will be more important, and that's usually what we're most interested in when we're trying to explain a model, feature importancy. You can also look at the SHAP values. If you don't know what this is, then really look into this. Also very interesting. And yeah, interpretability is usually so important if you're, for example, working in Microsoft Azure and doing your machine learning there. There are a lot of tools exist to investigate the explainability of your model, even when you have this black box model that you're using. Also, a good idea is always to change some inputs while keeping all of the other inputs constant, and then see what this does to your outcome variable, and this will give you a much better understanding about your model. This is not only to draw conclusions for the business, because the business usually is interested in how the model is working, but this will give you make you feel more secure in your predictions, especially in high stakes situations when it's really important to understand what your model is doing. So short, I'm not going from a highly complex model to a simple regression simply to make it more explainable. I'll use other solutions for that. Okay, so now we went through all of the questions that I usually ask myself. We'll go through a little example together to see my thought process in action. So this is a real data set that you can find on Kaggle if you've used it before, which is an online data science competition site. So for this data set, you want to predict house prices in dollars. We have 80 futures given, which are all related to house pricing, and then around 1,500 observations in total. So first step, are we doing machine learning here? Do we want to make predictions? The answer is yes. The goal here is simply to achieve the highest accuracy on the validation set and the unseen data set. So yes, we can use machine learning. Then is it a supervised learning problem or an unsupervised learning problem? This is a supervised learning problem because we have a labeled data set. The labels are the house prices. Are we doing classification or regression? We're doing regression here. Why? Because the house prices are in dollars, so it's a continuous value. And we already have narrowed it down a lot, so we'll be looking for supervised regression models. So not classification, and unsupervised might be useful in dimensionality reduction, but it's not the ultimate goal of this data set. Now, the amount of data, we don't have a huge amount of data. We have 80 features and only 1,500 observations. I wouldn't consider this as having a lot of data. So you need to think about improving your data set. We can't gather more data. I imagine maybe there are some public data sets available to get more data, but I don't think so. So the easiest way to get more data relatively to the amount of features is to consider dimensionality reduction and really using regularization to improve your models. The compute time is not super important here. We're fitting on our models offline. It doesn't have to happen. It doesn't have to be in real time. Is there a linear or a non-linear relation with our variables? We'll have to investigate this. We can do this during the data exploration phase. But since this is a real life situation in a high dimensionality, my assumption will be that it's going to be a non-linear relation, but we don't know this for sure yet. And the explainability, always important, as I mentioned before, but yeah, we're not going to keep it at a regression level, for example, simply to make it more explainable. We're going to use these other techniques that I talked about. So from these conclusions, first of all, I'm going to fit some linear models using regularization after I have identified some features that I think will be more important. So immediately I'm thinking about fitting some rich and lesser regressions. However, my assumption is that good models that also use regularization, good nonlinear models such as random forest or boosting algorithms such as XGBoost or AdaBoost will probably be better here. However, you do need to be careful to not overfit on your training set using those models. So really keep in mind that we don't have an awful lot of data available. So if you don't do this, then the regressions with regularizations might outperform those nonlinear models, even though there is probably a nonlinear relation with the outcome variable. A quick example, if I needed to fit this model in real time, so for example, if they wanted me to predict housing prices at each second, and we get new data each second, and we need to refit the entire model each second, then I'm probably steering away from these nonlinear models and I'm keeping it in a regression setting, but then I'll have to accept the fact that I'm introducing more bias in my models, so my overall predictions might be poorer but quicker, which might be more important to me in that case. You always have to consider what is most important for your model to really decide which algorithms will I be using. So some final thoughts, think about the no free lunch theorem. If you don't know this, then look it up. Basically, there does not exist one model that will work perfectly in all cases. You can't look at a problem and simply slap on some XGBoost or some deep learning, because if you always do this, then you will run into some very bad predictions. Also, you need to always think about all the possible algorithms that you can use in your use case before fitting any models, and then really think about does any model that I fitted behave unexpectedly? So, for example, is one model outperforming another model, even though I thought from all the questions that I just asked myself that one type of model would be much better? Then think about why this is happening. Maybe your assumptions were wrong, or it could also be the case that you're doing something wrong. So this is also good to consider. And then always interpret your results. This will really help you in the modeling phase. Thanks for thank you for listening. I hope you learned something today.